crystallization at the last. We use the crystallization is the last step to purify, and the crystallization, the product is solid. That's right. From previously, the solid product should be precipitation, and crystallization is the same. But the precipitation is we use at the very high concentration or supersaturation, and also we need some precipitant to induce the product. That's right. And also crystallization, we need only trouble or change the condition. That's right. Or add some additive to induce the crystallization. The concentration is lower than precipitation. And the product is crystal. I think you know crystal. Crystal is the pure substance. Right? Solid crystal is a pure substance, and then we can use the crystallization as the purified system. That's right. Purify. For the crystallization, we start from the solution. Right? We start from the solution, and that means we also define as the phase change. Right? The phase change from solution to solid. Sometimes we call the solution crystallization. Solution is maybe liquid solution, is maybe milk solution, is maybe gas solution. Like in the air also solution. Because in the air we have oxygen, we have nitrogen. This is the solute, something like this. And normally we talk about this, it is liquid solution. Right? When you separate the cell, you separate the impurity. You get only two components like protein and water, but protein dissolved in water. If we need the protein as the pure product, as the pure product, you can adjust the condition, adjust pH, or adjust temperature, adjust pressure, and then you can induce the solid. This is the simple process. Like you would like to produce sugar. You would like to produce salt like sodium chloride from the brain solution, from the sea water, from sugar from the syrup. This is the technique of crystallization. You will produce the crystal. Right. Okay. This is the example of the crystal product, like monosodium glutamate. It is also amino acid, and this is the derivative of monosodium glutamate. This is the derivative of glutamic acid. That's right. Glutamic acid is the amino acid, is the essential amino acid. This is the derivative glutamic acid. We use a lot of glutamic acid, and we have amino acid. This is one type of amino acid. The common company that's Ajinomoto. That's right. Ajinomoto is most, and the common company produce 20 amino acids. Glutamic acid, histidine, isoleucine, lysine, something. This is the amino acid, which is important for human in terms of the food additive, in terms of the drug. That's right. If you have some ill or has AIDS, something like this, you can eat the drug that contains amino acid. That's right, that contains amino acid. Monosodium glutamate is the food additive, like Ajinomoto. It is the famous. But Ajinomoto not only monosodium glutamate. It's many amino acids for food, for drug, for cosmetics. This is the crystal of alkylity. Right. There is sucrose. The product of the crystallization is crystal. Crystal means the pure substance. That's right. Pure substance. Only one component. Only one. Right. This is the definition of the crystal. Okay, when you talk about the solution crystallization is the purify is more than 99.5%. In the solution, we have when the crystalline, okay, when the crystal is crystalline, we have two phase from the one phase, that's like one solution, and then solution plus solid. We call it the slurry. After crystallization, from one solution to be solution plus solid. Right, from one plus solid. We call it the two phase slurry or magma. We call it magma. Magma is the combination of slurry or a combination of solid and liquid. Solid and liquid. Solid means a crystal. Liquid means a solution. Okay, and the liquid we call it matter liquor. This is a matter liquor, and solid is crystal. Crystal. And then after you crystallize, you can separate crystal or solid from the solution or from the magma. It's maybe use the filtration that you studied earlier, or you can use the centrifugation. As after you filtrate, after you centrifuge, you have to dry or you wash by the solvent. You get the dry crystal, and then you go to the package. Because this is the final step. You get pure solid. You get pure solid. And the advantage of the crystallization, because we can operate at low temperature. In low temperature, that you can minimize the thermal damage or thermal degradation of the heat sensible product. Heat sensible product, because the bio product is sensitive to the heat. But crystallization, okay, you can operate at low temperature. Okay. Before we talk about in the detail of the crystallization, I will show you the shape and size of the crystal. The shape and size of crystal is very important. It's very important, especially when you would like to separate crystal from the magma. The habit or the shape and the size. This is for the same habit. What is it? Right, the same geometry. Different geometry. That's right. It is very important. This is it. Sometimes it's difficult to filtrate. That's right. It's easy to filtrate. Sometimes if you filter have the hole like this, okay. If in this direction, okay, you can filter. But if it's flow, in this direction, okay, it's difficult to filter. Something like this. This is the shape and geometry or the size of the crystal is also important for the downstream processing, for separate after we crystallize. The shape and size or morphology of the crystal is the individual crystal and unique property for its substance. Right. For example, crystal with chunky or compact habit are easier to filter, as I talked to you. After it's chunky or compact habit, okay, it's easy to filter. And then you can centrifuge, wash, and dry. Okay, but the netherite, something like this, or twin crystal are easy to broken. That's right. When the crystal broken, this is not perfect crystal. Right. The crystal is broken. It's beautiful. It's not beautiful. Something like that. It's not perfect crystal. Because when you talk about the crystal, the gold, something like this, the gold, that's right. The carbon, so sometimes the price of the product is depend on the crystal morphology. That's right. The price of the product is depend on the crystal sometimes. For the pressed crystal, it's difficult to separate. The pressed crystal is maybe like this. Pressed crystal, right? Thing like this. It's difficult to separate for pressed crystal. Okay, this is the shape and size is very important for the process to separate the crystal from the magma. And another property that affects the crystal size is maybe density, right? Solid flow, the flow characteristic, the moisture content, the caking, the dissolution rate, and another like we call the filtration rate, centrifugation. This property also affects the size of the crystal and the size distribution. That's right. The size of the crystal and size distribution, I will talk to you later. What is size distribution? We talk about the size distribution because when you produce the crystal, right, sugar, sodium chloride, protein in industry, it's not only one crystal. That's right. It's many, because it's multi-particle. It's many crystals. We cannot produce all crystal at the same size. That's right. We cannot produce at the same size, but we would like to produce at the size that is close to the same, but not exactly the same. It's difficult. And then we can describe or we can measure in terms of size distribution. I will talk to you for the next one. Okay. For this case, mostly if we would like to talk about the size, sometimes we talk about to geometric property during its growth. Growth, what that means? We talk about the growth. If you would like to control the size, we should be growth the crystal. Growth means from the smaller size to be a bigger size. We can grow the crystal to be a bigger size with the same shape, different inside the same shape. You can do that by the crystallization. If initially we get a very, very small crystal, if you would like to obtain a bigger crystal, we can use the technique of growth. As I did the mechanism of crystallization. I talked to you in the next topic, the growth and nucleation. For this, we can control the size by the growth. How to measure the growth? We measure by the size, like the characteristic length of L. What that means the growth, it means the size increase with respect to time. It's the rate of growth, something like that. Okay, for this case, we can represent the crystal size in terms of the crystal size, surface area, volume, and mass. As I define in terms of L, in terms of the characteristic length. For example, AC is the surface area, which is equal to Ka multiplied L square. The L square unit is the length square, this is area. Area, and then you calculate this by multiplied by the area shape factor. And volume should be KVL power 3. KV is the volume shape factor. Okay, from this relationship, we can calculate the mass. You can calculate mass by multiply volume by density. You get the volume. You get the mass, something like this. And then how to calculate factor. In this, I show you the shape factor in terms of area shape factor, the volume shape factor. I think it's very difficult to identify because the crystal is like it's not the cubic, it's not cylinder, it's not the sphere. The crystal in the nature is very, very different. It's very different. It's not the basic shape, right? Like sphere, like cylinder, no. As I like the cube, like this. This is the basic. But for crystal in the nature, it's not fully like this. It's many, that's like many shapes. For example, this is the one of the example of the crystal. The one example crystal. Okay, for this case, we use the maximum size and maximum length and minimum length at the L. That's like for Ka. Ka is the AC divided by the LA square, or AC divided by the LB square. LA is the minimum length. LB is LA. This is LA. Sorry. Right. The maximum. That's right. And LB, the minimum, something like this. We can identify for the Q. Okay, the Q is easy to define. This is the maximum length. That's like this LB. Right, this is the definition of the area shape factor for the case. Area shape factor for sphere, for cylinder, and for cube, okay, it's easy to calculate. But for another shape, okay, it's difficult. You have to find what is the maximum length, what is the minimum length. You can identify that. But more for this case, you can obtain from the resource, from the reference book, from the reference data. You can obtain from that. Okay. Another property that we can find a lot in the biological product, we talk with it, polymorphism. Okay. Polymorphism means the same chemical, like glutamic acid. It's also glutamic acid. But when you crystallize in terms of solid, if you obtain the crystal, it's maybe more than one crystal form. Like for this, the rod line, it's maybe the prism, different shape, but the same crystal. For this case, the polymer in the different shape, the same crystal, different shape, the same chemical, the same chemical. And different crystal shape of different crystal morphology is also different in physical and chemical property. Like this with solubility and dissolution of the crystal is different. The density is different. The melting point, the color is also different. Like this. This is the property of polymorphism. When you apply in the drug process, that's right, the drug process, the form that higher solubility is also needs or the lower sensitivity, it's up to the application. If it's higher dissolution rate, it's easy to dissolve in your body, the drug, something like this. We may prefer the form that higher sensitivity, something like this. This is the term of polymorphism. Like I show you the polymorphism of the histidine and glutamic acid, like this. This is the term of the crystal form in unit cell in the chemistry that time. We have 1, 2, 3, 4 molecules in form A. That's like crystal in form A. And we have 2 molecules in form B. The shape is longer and look like the lot. It look like the plate for the form A and form B. That's right. This is L-glutamic acid. It's different in crystal structure. That's right, in crystal structure. And this I show you the crystal obtained from the real system. That's right. This is for form B. This is from form A. It is maybe plate line. It's lot line, but different shape. Different shape, also different physical and chemical property, also thermal property also. Right. Each shape, each form is applied in different, that's right, applied in different applications. Okay, the next important, we talk about the site distribution. I talked to you already why we have to know the site distribution. Because we cannot produce only one side of crystal. We cannot produce the sugar at one side. We cannot produce the sodium chloride at one side. That's right. But we can control the side of the sugar or the side of sodium chloride. It nearly occurs to the same. We call it uniform inside, something like this. You can check in the market in Big C, Lotus, or in the minima, and you check the side of the sugar. It's close to the same, but not exactly the same. That's right, exactly the same. Because we cannot measure all the crystal size. We cannot produce all the size or the crystal have the same. For that case, we can measure in terms of particle size distribution. Distribution means many size of crystal. Okay, if we plot the size, but sometimes we plot the percent, that's right, percent of crystal or percent volume, percent by mass of crystal. Okay, this is about 8 centimeter. Mostly we hear about micrometer, that's right, micrometer. It's maybe 10%, something like this. And this is maybe 20%, 50%, like this. This is 9, 11, it's average. 8 micrometer, 9 micrometer, 10 micrometer, 11 micrometer, it's average. And then you can do the distribution of the size. That's right, distribution of the size. But for this case, we would like to control the distribution of the size should be like only one line. It's difficult. That's right. It's difficult. Mostly we can control it narrow in distribution. It's like this. Okay, it's also good. That's right. Sometimes we get like the narrow distribution like this. Sometimes we have the more narrow, something like this. But we would like to the narrow distribution. That's right, narrow distribution. But the idea we need only one. That's right, only one side. It's not possible in the real system because we cannot control to produce sugar, to produce sodium chloride, only one side. Okay, we only control the side distribution is the narrow side distribution. What is the technique that we can use to measure the side distribution? The basic, simple, we use the seed, right? The seed. I will talk to you like the filtration. Or you can use the microscope. But microscope is not 2 diameter. Or you can use the particle vision or measurement PVM or matricizer or FBIM. Or this we use the technique of sensor or the light. That's right, to protect the crystal, the automatic side. In my lab, we have this to measure the particle size and microscope, and also the screening light. But most industrial, we use the basic equipment, like we call that the screening, seeping, or screening. This is the basic. That's right, it's the basic, but not automatic. Like this, we can use the microscope. That's right, the microscope. I measure the microscope. We have the scale, but microscope is 2 dimensions. That's right. We can only measure this direction, but not in the depth. That's right. We cannot do that. And also, you can use the microscope count the number of the crystal. We can use the microscope to measure the number of crystal for nucleation rate, size of the crystal for crystal growth rate. This is the 2 mechanisms we talked to you in the next. That's right. Okay. And another, we use the light scattering. Light scattering, we use the Malvern or magnetizer. We use the light technique. That's right. In HUT, a lot of this equipment, but not in my lab. In my lab, we have FBI. This is also FBI, MPVM, and magnetizer. This is the technique of the light scattering. Light scattering. Okay, the most common used in industry and it's cheaper when compared to the automatic equipment. It's cheaper and used for common industry. Because this is the screening analysis, the SIP. That's right, the screening analysis. Okay, I'm not sure you will do this laboratory in the unit operation. I'm not sure, but you study this to decide the screening, and also we have the SIP a lot of in the site. That's right. Okay, for this case, the crystal size distribution determined by the Y-mate screen. That's right. Crystal size is checking to be the screen aperture opening for each screen. That's right. For example, we have the screen. We have the hole or opening. That's right. Opening hole. It's more produced from the aluminum, from the metal. That's right. Compared to the chemical, something like this. Okay, for this case, the particle that is larger inside than the hole cannot pass through the side. But the particle that's lower inside than the hole, okay, can pass through the hole. But for this case, we have more than one. As you made in the later, is the top is the bigger one, smaller. That's why we have many sides, and then you can cut the side. That's why you can cut the side. You have many sides of the screen. This is for the US standard. US standard, the SIP number 4 is maybe the mate number 4. What is the opening size of the hole? 4.76. This is the diameter of the hole. The size that is higher than this size, okay, will accumulate on the SIP. The size is lower, it will pass to the next screen. If we use the next screen, is number 8. The size number is mate number 8. The whole size is 2.38. If the size from the previous mate, previous screen is between 4.76 and 2.38, this particle will accumulate on this screen, something like this. If the size is less than this hole, okay, it will be passed to the next side. Pass to the next seed. Okay, for this case, we can do many seeds in the radius from the bigger to the smaller, and the bottom it should be the pan. Pan means the seed that no hole, no opening patch. That's right. Okay, this is the technique of the screening. Okay, and also we talked before about the screening analysis. We have many shapes of the particle. It's very important. That's right. It's very important. Okay, for this case, okay, it's easy to separate by screen. It's also, but for this case, right, if location like this, but if we cannot screen, that's right. For this also, we move in the different direction. It depends on the direction of the side and or depend on the size and shape for the screen. This is the difficulty of the screen analysis. It depends on the size and the shape of the solid to be separate. Okay, how to analyze? That's right. For that case, we have like the screen number 1, number 2, number 3, number 4, and pan. This is pan. Right. It may be number 4, number 6, number 8, number 10, and pen. It depends on you can use the shape for all, or it may be number 4, number 7, 16, and pen. It's up to you. Okay. And then you use the vibration, and then you have analyze. Okay. How many math in this? How many math in this? That's right. How many math in this? You calculate the math that accumulate on each screen, on each sheet. How to calculate that? The delta W, that's right, delta W equal to the delta math divided the total. Delta math means amount of math that accumulate on each screen divided by the total. You know the total math at initially. Okay, for delta M1, sorry, delta M2, delta M3, for example. Delta M means the math that accumulate in this screen. That's right. You get the delta W. And then you can calculate mass density distribution. Mass density distribution equal to delta W divided by L. This is delta M, MT, and divided by delta L. That's right. What is delta L? Delta L is the difference in the size of the opening. I will back to you. If we use the screen number 5 and number 10, that's right. The size of this 2 and 4, delta L equal to 2, something like this. Is it the delta L for that scale? Delta L means the difference inside of the shape at lower and upper. That's right. Okay. Okay, the result after you analyze for all the shape number, you can plot linear graph by the average of the particle size. Right. You can average the particle size, and then you can calculate the maximum value of the mass density that we found this dominant side. For example, we talk to you in detail to understand it like this. For this case, we use Taylor seed, like 1, 2, 3, 4, 5, 6, 7, 8 seed. Right. This is we use the seed by the Taylor standard. Previously, we show the US standard. This is the Taylor standard. Okay. 24, 28, 24, 8, 33. We use this seed. Right. 65, 100, 150. 65, 100, 150, and 200. Okay. Okay, this is we use this method. That's right. We use this method. Okay, the size is maybe on inch or on millimeter. That's right. This is the size. This is size. Okay. Okay. And this is the math that retain or accumulate on the screen number 24. That's right. This is the math that accumulate on the screen number 28. There is no solid accumulate on screen number 24. 0, that means no solid, because all of the particle is smaller inside than this number. That's right, than this number. And 0.05 gram of solid particle it accumulate on this number. That means the size is between 24 and 28. That's right. How much? What is the size? You can look at from this. That means about 0.05 mass, 0.05 gram of gram of solid. Right. Is between 0.02 and 0.027 in or 0.7 and 0.58 millimeter. That means the size of this solid is between this particle. It's between this size, like this. And the next one about 1.05. 1.05 is between 28 and 35. That means the size of this crystal is between number 28 and number 35. You can see that. It's between 0.232 and 0.0164. That's right. The size of this crystal is between these two sides, or these two sides, for example. Okay. This is the mean. Okay. Okay, the question is plot the mass density. That's right. Density distribution using histogram plot and by the line plot, and then this means the dominant crystal. That's right, the dominant crystal size. Okay, this is the mass density distribution. Calculate this. You know the mass in each page number is the three number. You divide it by total mass and divide it by the delta L. You get M for each rank. That's right, each rank. Okay. For example, if we calculate the delta W between Taylor screen, okay, 100. That's accurate on the screen 100. Look at 100. 100 is 21.6 mass of the crystal. That's like accurate on the screen number 100 is 21.6. And what is the total? Total, you have sum up of this. Sum of it, you get about, this is the total. That's right. This is total. This is the mass of crystal accumulated on the Taylor screen number 100. You get delta W equal to 7.237. That's right. Or you can calculate it's about 23.7%. That's right, 0.7%. And what is the size between this? Mass number 100. You check the size between 100 and 65. Right. This is about 0.0082, 0.085, or this, we have to use it in millimeter or in inch. Okay. The size between 147 and 208 centimeter, that's right, centimeter, 0.147 or 0.208 centimeter, millimeter, sorry, like this, millimeter. 0.208, 0.147, or 208 micrometer, 147 micrometer. This is the design. That's right. It's because between 100 and 65, no 80, because we use only 65, 100, no display. That's right. No display. Okay, what is the delta L? Delta L is the difference between these two sides. You get delta L. That's right. You get delta L. Okay, and then you can calculate M equal to delta W over delta L. Delta W equal to delta M over MT. This is the W. You divide it by this delta L. That's right. 208 minus 140. You get this value. This is the mass density distribution is between mass number 165. You can do this for all of it. You can do this and this. This and this and this. All of the cluster, that's right. You get the mass density distribution. Okay, like this. All right. Okay, for this number 24, this is the size. 28 is the size. The size. Okay, size. For pan, here is no size. It's zero. The size is zero. And the increment, that means delta L. This is the delta L between this. That's right. This delta L between this. And this is delta L between this. This. Okay. This. Okay, this is the delta L. Okay, this is delta L. And mass retain. Mass retain you obtain from this. That's right. This is mass retain. And then you calculate delta W. Delta W is mass retained the delta M divided by M total. That's right. This is the M total. You get for it. All right. And mass density delta W divided by delta L. That's right. This, sorry. This divided by this. This divided by this. This divided by this. All right. All of this. You get M. This is M. That's right. And also you calculate average. That's like L average. Average is the average between this. You get this. This, you get this. Between this. Right. You get this. This is the average. Okay. The first you plot the particle size with the average. Okay, for that case. This is the particle size. That side. This is from the 0 to 0. This is 0 to 44. 74 for 104, like this. Right. It is 0, 74 and 100, 104, like this. And it plot, and this is between 0 and 74, like this value, right? And this is value. This is value. We plot this. That's right, we plot this. This should be average, like this. This curve, this. That's right. Okay. You get this. This is the size distribution. And also you can plot the average. This is the average from this and this. Right. You get this curve. And you plot between this and this and this. With this, you get this curve. We call this the histogram. We call this the line force. We do average and particle size. And then you can determine the dominant size or maximum. This is the maximum point. Right? It's LD. It's the maximum size possible. Okay, I will break for 10 minutes for that case. If you have any questions, ask me for the 10-minute break. I will continue this for after break.